Of course, of course. This is an exciting actually event. It's now time for our first panel discussion. And our panel will consist of the speakers that you just heard from. So John, Smithy, Jason, Lou, and Aiko. And additionally, we have two invited panelists, Professor Kirsten Peterson from Cornell University and Professor Annie Shea from University of Pennsylvania, who I see are already joined, and are co-host. So you all should be able to unmute yourself at this point. And before we start the panel, actually, let me remind or suggest all participants to switch to the speaker view on Zoom. You can do it on the top right of your Zoom window so that you can enjoy the panel discussion more. And the panel discussion will be chaired by Professor Shea. So Annie, you can unmute yourself and feel free to take it away.
Great, thank you so much. This was a great sort of set of talks to start us off. And so let's see, do we have, I'm trying to see if there's a way I can get everyone, there we go, okay. I'm gonna switch to my cat, there we go. Okay, so I'm gonna kick this off since I know that there's gonna be lots of questions coming in through Slido. So I am going to start us off with John, and I think it's a nitty-gritty detail, but maybe this is a way to kick off this question about the magic number that is 20 that you have picked for your simulation environment. Let's start with that.
So, I mean, I should have scanned the audience to see who's actually here before I drop names here. I will be totally honest. And the number 20 actually came from a program review we did where Mark Steinberg from Navy Research Lab was in the audience. And many of you might be familiar with Mark. He's a program manager for a huge range of multi-agent autonomy programs over multiple decades now, probably. And he threw out this number of 20 robots because I think it was sort of this idea that like we've seen pretty compelling, like across the board, whether it be like you think about like the DARPA sub-T kind of examples of like we're going in, we're building maps of underground environments. We see compelling results in the like 5-ish range kind of robots. And then you look at even in the case where like we're talking about like let's throw out a bunch of quadrotors and have them do like real communication to achieve a task. You see these examples and they sort of like just sort of anecdotally kind of cap out around that like 10 to 15 kind of number. And you go beyond that if you're doing real communication, that is like anything other than just like a broadcast architecture where you just broadcast everyone and they do the thing. You start to run into some serious like limitations in terms of just simple things like congestion and latency of your comms. So that's where that number 20 came from. I don't know if it's the right one, but it's a number.
So I'm going to throw this to Heiko because I think, since you were talking about swarm density and there is some, pretty interesting sort of work that has been done from speakers today as well as organizers. So just want to hear your thoughts about that.
Okay, so thanks. It's kind of a bit of a tricky question, of course. And so if I get it right, we are discussing right now, like what is like the minimal number to have a swarm, or what is like the number once it's really challenging. And so I'm teaching a course on collective robotics or swarm robotics, and we have some definitions there on the slides. So you can find in the literature all sorts of like funny definitions, like whether it's several hundreds or it's like something. If you would want to model it, then you need like actually do some statistics. So you would have a macroscopic model and then only model densities of robots because you can't even afford to model each single one of them. And so then in the exam, we do our exams here, and then I would usually just do that as a conversation starter, right? I would not look for a number, or if some student would say like 5, then that would get me started, right? But I think what's important is like for this definition, it's just about like, do they behave correctly? So is it swarm behavior what they're doing? And maybe to connect it to what John just said is then, of course, in terms of communication, so local communication would be a requirement. Like if you have all-to-all communication, you can actually afford that, well, go ahead, do that, right? So you're fine. But then maybe it's not really a decentralized system and probably not a swarm. Let's see what I can say a bit more. I mean, scalability is a thing. And then, yeah, in terms of density, well, most of the time I think like this like swarm, the swarm performance curve that I've shown, which is actually like performance, whatever performance is over swarm density, robots per area. Or you could do it as like coverage, right? Like, so what is the communication range and how many robots can you fit within that, or do you fit right now? And I think this is actually quite generic concept. So I believe you will always run into these curves, not actually only in swarm robotics, also on a highway or on a parallel computer or something. So that's really a rich concept, and it's about like congestion. At what point is some resource that you share not available anymore? And it could be the communication channel, but it could also be space, right? They share space, and at some point you will run out of space. Everybody's just avoiding each other, as you would have in a wireless sensor network, right? But just not communication channel, but the limited resource is space. So these scaling problems will always appear, and I think it's always relative to the particular scenario, but it will always be there, I believe. Yeah.
So sort of, move sort of using that as the point, to jump off to something that is related. So we're talking about shared resources. We're talking about basically bottlenecks, right? In these shared resources. So Christian, I'm sort of interested in hearing your side of things, given the fact that you, right, sort of are more on the hardware side. And how do you think about, these kinds of constraints and these, issues of scalability and how the hardware then sort of interacts with the software?
Yeah, thanks, Annie. Yes, you're right. So my research, I mean, we certainly, we all need models, right? But you're right. Like my research focuses a little more on what do we get when we actually have real robots, embodied robots, and sometimes not even robots at all, but actual honeybees that we try to turn into robots in the field. So when we do real robots in our lab, it's anywhere from say 5 to 20. When we do our honeybees, we're in the hundreds. At least, the full swarm is on the order of tens of thousands. I think, okay, so first of all, if you have hardware, and I think it was mentioned many times throughout the morning, you automatically get heterogeneity, right? So as the robots continue to operate, they automatically differ slightly. And so you get some interesting interactions. I think it depends a lot. Like if you're targeting systems that do, if you're targeting drones that operate in close vicinity, but not physically interact, the difference between 5 and 20 may not make a big difference. If you're operating like Dan Goldman with things that physically hit each other, you might actually need hundreds of things to show the full macro scale behaviors. For us in our lab, I think, that's another thing, right? For researchers, obviously, there's just a fundamental limitation to what we can practically entertain in our labs and maintenance for swarms is really a big issue. One of the interesting paths that my lab has recently gone down, and I hope more people will follow, is if you have robots that modify the environment, like what Heiko is doing, for instance, right? So robots that have to act in the real world, but try to help themselves by modifying the environment slightly in order to have an easier time reasoning about the world. Errors scale really non-intuitively, and it gets really interesting as the number goes up. And so once you don't just have robots, but robots and physical interactions with physical objects in the real world, the number becomes a whole different, it's no longer 20, right? And there can be a very big difference between 1 and 5 and 20 and 100.
That's great. So that sort of moves us on to something related, right? So this is probably something for Smitri and Jason, sort of, you guys have a sense of, or opinions about hardware, specific hardware and sensor developments, especially in the last, in the recent years, given how fast new things have come online, that, greatly aided and made the deployment of large numbers easier? Any thoughts on that?
Yeah, I can start there. So I think what helps with our deployments the most is very mobile robots. So our robots are multiple tons, which makes you think about sluggish robots, but just having robots that are nimble using new types, like SICK has a new type of safety rated scanner that has 128 field sets on it, excuse me, and that allows us to do more complex but safety rated navigation. And so this allows us to treat our very, very big robots as nimble as a small robot might be. So whereas before it might not have been feasible to use some very clever and tricky dynamic algorithms, now we can start considering those. We're also looking at new types of hardware around direct communication. So there's 5G modems that you can put in robots now that give you very high bandwidth, low latency communication. There's Bluetooth that gives you nice direct local point-to-point communication. Yeah, and just like 10 years ago, these were not things that we could consider. So it's just nice to be able to take things that we could look at in the lab maybe 10 years ago and theorize about and actually deploy in the real world.
Excellent. So here's another question. I'm just sort of, feel free, any of the panelists, feel free to take this, right? So I think Kirsten sort of hit on this, and I think everybody hit on this to some degree. So the fact that you have more than one naturally introduces, right, heterogeneity into this mix. But there is sort of, small variation in heterogeneity and large variations in heterogeneity where you're now really thinking about, platforms with that basically operate in different parts of the workspace, right? So I'm thinking aerial vehicles, ground vehicles, so those kinds of things. And so when we think about heterogeneity, right, sort of the range of heterogeneity, it seems that we have work that sort of can handle the small variations in heterogeneity. We can handle large variations in heterogeneity, but maybe not in this large number of agents. And so in that regard, what do you think are some of the open challenges when it comes to these issues of scalability and shared resources and constraints? So I'm going to throw it to John to start us off.
Trying to wrap my head around this. So I mean, just to make sure I'm understanding the question correctly, you're trying to sort of get at this like degree of heterogeneity and how that influences the solution.
Yeah, I think that, or how that can, that potentially, I think constrained is maybe the wrong word.
Okay.
But right, because I just, I think we think about heterogeneity in the sense, what I would say variations in individual parameters, right? That's one way of thinking about heterogeneity. Maybe that's a little bit easier to handle versus, something that are just really about you have, 2 different types of robots or 3, 4, 5 different types of robots and very different sensors.
Yeah, sure. So I mean, if I go back to the way that I was describing things when we kicked off this morning, this is exactly the type of scenario that, in my mind at least, is like what pushes us towards these architectures for swarms or multi-robot systems. I like to say multi-robot systems, but it says a workshop with swarms in the title, so I'll say swarms. In the sense that I think being able to explicitly do like allocation and planning for the different like morphologies that your platforms have, the different capabilities that they have, I think is really important. I think that's what's going to be necessary. I mean, I think back, even you can take some like really simple examples of things like consensus algorithms and things, and you think about the graph topology kinds of questions, and it's the type of thing where you can show these really compelling results where like one or two long-range communication links vis-a-vis like a higher powered radio on one of your robots. So heterogeneity in that aspect will actually show you like way improved convergence results and things. And I think being able to explicitly design for that is actually really important. I don't know that I necessarily have an answer of how to best marry that with like the sort of the nearest neighbor control law, which are type of ideas, which are typically more like they're based on homogeneous platforms and capabilities.
So I'd be interested in hearing Lou, what Professor Lou thinks about, in terms of how diverse the range of heterogeneity can be, and how we can push sort of some of the more control theoretic strategies.
Thank you for the question, and I think that's a great question. Honestly, as you see in my slides, actually, currently we only consider, as you said, that small heterogeneity, and that is easy to be dealt with, well, theoretically. But I do think it's very important to consider like the more differently, like different agents. For example, sometimes, as John also showed, sometimes we need the ground robot and the UAV on the sky, and they need to cooperate together. And those kind of problems, I think those are very important. But so far, theoretically, we haven't considered that yet. And the current result actually heavily depending on the dynamics. So we need to know that. So one possible way that I can think of is probably, well, you all know that in recent years, the so-called the AI or the learning algorithms is getting popular again. So probably by using that, we could adapt to more heterogeneity or model-free or kind of thing. Yeah.
Great. So Heiko, you had a comment.
Yeah, I just would like to give it a little bit different twist. I mean, these ideas of heterogeneous swarms, like they are designed to be heterogeneous, right? I mean, there have already been some really interesting projects like combining ground robots and drones, and that's beautiful and probably really something we want to look into. But I just thought like whether it's maybe interesting here to think big, right? So what if you consider not like heterogeneous swarms that were designed for being heterogeneous, but they just happen to be, right? And there's a beautiful paper from like, don't know, what is it, 2 years ago, appeared in Nature on machine behavior. And they touched all sorts of subjects there, but the idea, like very condensed somehow, is something like we have all these artificial intelligence systems, we have robots and everything, and they form, after deployment, they happen to form an ecosystem an ecosystem of systems, right? And they influence each other, and it's impossible to predict what they will do. And so I was thinking, maybe that's also something we should think about. What if like we have two robot swarms that were designed as homogeneous swarms, but then they happen to run into each other at some point after deployment, and can they deal with it, right? Okay, they can avoid each other, but maybe they can also collaborate and help each other. And I think that's a beautiful idea, and that would be definitely worth looking into. Like, you can't really prepare your robot swarms for that, but what they claimed in that paper, I think, was mostly because machine behavior, of course, should remind you of animal behavior, so that you need methods from animal behavior to study these systems that like emerge after deployment as heterogeneous swarm, if you like. And I think that's really important, and someone should start looking into that, because we will have more and more robots, and they will just run into each other, and they will have to deal with each other, and making them like heterogeneous by accident.
excellent. That's a very, very interesting insight. I mean, in some ways, it's kind of, it reminds me of Arkedio's work back, you know, a while back ago, right? We think about, oftentimes we think about heterogeneity in terms of hardware, but we're really talking about heterogeneity in terms of behaviors at the robot, at the collective behavior level. And I think, Heiko, you actually, you know, sort of hit upon this thing. So we have a lot of questions from the audience that are thinking, right, in terms of, you know, sort of numbers and thinking about sort of scalability, what we mean by that, but also sort of, you know, asking questions of when do we think we're going to have, you know, 100 or more robots being used together. And in some ways, it sort of reminds me of this phrase, and I think some of us, you know, who are old enough will probably remember the phrase systems of systems, and how we are kind of heading into, right, this notion of systems of systems, and how does one go about designing and figuring out sort of the complexities and dealing with the complexities of systems. Anybody have any thoughts? Any of our panelists?
Can I give a quick comment?
Of course.
I was just, I mean, it's an interesting notion, right, with the big numbers. Of course, there has to be an idea for a research lab in deploying a big number. If you can show the concept with fewer, it's definitely what you should do. But we've also, in our lab, recently taken more to the field in collaborations with others. And I think it gets really interesting, just based on this talk we just had about heterogeneity, when we place robots in the real world with real ecosystems, just like Heiko just said. So as an example, we're trying to look into how we can monitor pollinators, which is sort of an essential service worldwide. And for that, we have, you know, both robots, we have camera traps, we have people, we have, like, you know, the full scale, and it becomes almost more of a cyber physical system where it's not necessarily emergent behavior, but you're going to get emergent behavior because there's just so many agents. And what I think is possibly important in those tasks is that they're not necessarily completely complementary, right? It's not ground robots and flying robots. They're agents that have overlapping capabilities, and some are better at some things than others. But it gives us a lot of robustness in the system, right? And it means that in some cases we can go for, you know, efficient operation, or we can go for more robust operation. And I think once there's overlap in those skills, everything gets a little more fun. So I think, you know, when you go towards Swarm, it doesn't have to be 100 robots. It can be, you know, 20 robots and, you know, whatever, 60 plants and 40 bees, or, you know, whatever you're targeting. It can be 20 autonomous cars and 80 non-autonomous cars, right? But the system becomes complex at that point.
Any other comments from our panelists before we, you know, John probably has thoughts about this, given sort of his involvement with the ARL program.
You're speaking about numbers of agents?
Numbers of agents,
yeah.
Sort of this notion of a systems of systems, right? I think in some of your talk, you know, well, we talk about coordination of large numbers, but sometimes it's coordination of smaller numbers, and then coordination of those smaller numbers.
Yeah. I mean, in some ways, like, I think that the second task, the defense task that I talked about, you could think of as like a hierarchical architecture, if you will. And in some, I think it was Heiko's talk where he referenced some of Sid's work on this idea of swarm density, because I think that is, like, for me, that is a driving principle that I've even started to, like, sort of revisit as we think about some of these things, because I realize from some perspective, or from my perspective, from the ARL perspective at least, like, I don't really care about the number of agents. I care about the task that we're trying to achieve, right? And so it's one of those things where it's like, if I'm talking about searching a building or searching, like, a football field or something, I don't need 100 robots to do that, right? I can put 5 robots up there and achieve the task. And so trying to come up with solutions for 100 robots in that space actually doesn't buy us a lot. And so that's something that I think that's important to think about. And I think this meshes in with these same ideas of heterogeneity, and either heterogeneity by accident, or like what you get when you interact with a complex system in the field, is this idea of, like, I think what's really important is for us to sort of, like, maintain that eye on the prize of like, what is the thing I'm trying to do? And then what is the scale that's necessary for me to achieve that? And it could be that 100 robots in like a 10 by 10 meter square is going to be really, really hard for communication because of congestion or something. But you take those same 100 robots and you spread them out so they can only talk to 1 or 2 neighbors, then the communication problem is not as hard.
So here's another interesting question. So what is the impact of heterogeneity on that performance curve? So that I think that's probably a very open question at this point.
I can try to say a little bit about that because I also saw it in the list and it made me think, so that's good. I try to be short. Each like whatever this heterogeneity means here, but let's say you have like subpopulations in your swarm and they have different requirements for different shared resources, right? And so for some reason for now, it would be easier for me to think of like a computing system, like a distributed parallel computing system. And, you know, some like share some memory, some don't, and you have, don't know, a printer system and whatnot. And then they have all different requirements. And then that helps for sure to increase scalability. But then, I mean, if they're not totally complementary to each other, so they actually do share still some resources, then you would still run into these kind of problems, but maybe in a more complex way because now they behave differently. They have 2 subpopulations at least, and you have to manage that. But I think it's a nice thought also, like as a method maybe to like push scalability even further. That you have some robots that are happy with scarcer resources and others who are a little bit heavier on that, and then try to like, let's see whether that manages or solves the problem, right? I like the idea.
So one thing that question reminded me of was some of Arkadio's earlier work, right? And so in there, they were thinking about, you know, what they've noticed is that this notion of specialization and sort of, and you know, you can start out with a homogeneous team, but then you end up, you know, through these interactions, you can potentially get them to specialize and effectively, you know, diverge in terms of what they're good at. And so that's another interesting thing and how that plays into the performance curve will be another big interesting question. So given the fact that, you know, we have, we're just about, you know, sort of heading towards the end of the panel discussion, I wanted to throw out this question. I'm going to give everyone a chance to answer. So what do you think are some of the open questions that you're excited about moving forward? And what are the, you know, and sort of what are some of the advice you would give sort of young researchers who are interested in making, you know, a big impact in this area? So I'm going to start with Professor Liu.
Yes, thank you. Well, again, it's my great pleasure to join the panel, and I see so many different people and different ideas. And talking about the open problems, I do feel that it's related to what we just discussed about. I think, well, first, if we talk about, take the number of the agents, for example, I do agree with John that, so how many is enough or how many is necessary for our, like the task or the mission. So I think it's quite interesting to consider. I mentioned briefly in my talk is well, performance or the performance curve you just mentioned. So do we, well, at what circumstances do we, like how much we care about the performance, or do we need to reach the optimal performance, like, or the trade-off between our cost or the how many agents we need, or the communication cost, etc. So I think that is, again, because we focus more on the algorithm part. So I'm quite interested in how to implement these algorithms to these real world problems or experiment. Then I think when implementing those algorithms, we will face the problem to take care of to deal with the trade-off. So that part, I think it's very interesting.
Thank you. I'm gonna go next to Dr. Smitri Chopra.
Yes. Hi. Sorry.
Okay.
Internet is a bit wonky. My advice to young people coming in would be that, this is an incredibly exciting field, and it's also very, very creative, and it's not immediately obvious how you design these solutions. So especially in the industry, especially the kind of industry I was talking about, material handling, it is also relatively untapped. So I would say that bring all your creativity and vigor and go try exploring this space, and definitely bring new stuff here, because we need to see more. Academia is great, but jump ship, basically. And ClearPath is an amazing place, so do consider joining that.
No.
Sorry.
As an academic, I'm trying to encourage my students to go into academia.
Oh gosh. Okay,
Maybe let's take this discussion out of the panel.
That's right.
Yes. I'm sorry. And as for open-ended question, I'm gonna take a hard turn here. I have recently left the field of industrial swarm robotics, and I'm now actually exploring game design and game AI. And I am very excited about bringing swarm robotic concepts to game development. I want to see emergent behaviors between different characters and, players and dogs, mice, cats, that kind of stuff. So for me, at least, it's very unexplored in that area. I know it's a really hard turn from this conference, but I'm sorry.
No, that's fantastic. So Professor Heiko Hamann, your turn.
Yeah, thanks. So I have really this one. I could almost like print it out and put it at the wall in my office. So I think with swarm robotics, we've played for long enough in the lab, right? So I mean, I've done that for don't know how many years, and I'm sick of it, right? So it's enough of these toy robots in the lab, and it's really difficult to do new things. I mean, you can always develop really like beautiful, nice new algorithms and then showcase them. But in the end, you have toy robots in the lab, and then you have to explain to people like, yeah, what is it really good for, right? So I would highly recommend, so if you are new to the field and you have some freedom of like what you want to do, then try to get out of the lab, right? So can you do a robot swarm in the wild, and even off-road, right? So not just put some big robots on paved ways, right? But put them out of the lab. That immediately triggers a challenge or many challenges. And one of them is also what we discussed before, and then also what John, I think, addressed explicitly. Okay, can you afford off-road robots, buying them off the shelf and then invest $100,000 or something to buy 6 of them, right? So I think one beautiful challenge would be coming up with some nice hardware designs, for example, for new outdoor off-road swarm robots, and you could go crazy there, right? Be creative. So I've seen there's like many of these papers where people do robots, like again for the lab, but it's like just a little block with 2 servos, and it has like 2 little wings. They can't fly, and they can just like flap them a little bit. One can't move at all, but if you put some of them together, they start moving, right? So think like this, like, can you build something? You just build some funny kind of shape with some actuators. You put them together out there and into the forest or whatever, and then they happen to do something useful together. And I would love to see something like that. Also, you could go to water, so like surface vehicles for water are maybe easier to build, to design, also for cheap designs. And I would highly recommend to try to do something new outdoors, because there it's much easier to do something new.
Thank you. Professor Kirsten Peterson.
Sure. So I guess my advice to new people is think super interdisciplinary. Be open to conversations with people from every single field, because even if you want to focus on just algorithms, you're going to learn a lot from talking to people in bio and people, you know, from earth sciences and people who do hardware all over the place, right? Really, I think this is a field that benefits even more so than other fields of robotics from interdisciplinary interaction. So take extra time out of your workday to browse for interesting articles, to go to interesting talks, even though it takes away from your direct research capabilities. I think for multi-robot systems, that's really, really critical. So I'm not going to repeat what Heiko just said, but yes, absolutely, we should definitely go out of the lab. But I think also I would love to see more people, and I am myself focusing on like what really happens when robots are introduced to really hard environments. Can they, instead of just having all the sensors necessary to deal with those environments and all the perception and reasoning capability able to deal with those environments, can they just slightly modify the environment to suit their own purposes? And it doesn't have to be, you know, static artifacts. It doesn't have to be moving bricks around like Heiko showed. You know, it could just be creating airflows that other robots can help, or you know, fluid if you're in the water. But really sort of looking at how can robots engage physically with their surrounding environment in order to coordinate better.
And Dr. John Fink.
So what Heiko said, get out in the real world, do real things. Maybe like a corollary to that, which is sort of what I was saying before, is like, I think there's a trap to fall into that's been fallen into with a lot of swarm robotics, of like say like the example of flocking or something, like where it's like you're kind of doing a task just for the sake of doing the task. I think we're ready in this field to like make sure that no matter what we're doing, we're actually solving like a real world problem, or like a complete problem, if you will. And maybe my corollary to that, which is more like a personal advice, is just like, make sure you're having fun doing it. Like, you shouldn't be working on a problem in this space if you don't find it to be like the most interesting thing. And so I don't know, that's what I've used to guide that for my work for quite some time. If I'm having fun, it's usually means I'm in the right spot.
That's a great lesson. It's a great piece of advice for just everything in life in general, I think. So I'm just gonna so we have 4 minutes left, and given the fact that this question has been upvoted by the audience, I'm gonna sort of put it out there, and I will let any of the panelists feel free to take it. So when applying multi-robot and swarm systems in the real world, do we have a grasp on how we can deploy and maintain hundreds and maybe 1,000 robots or thousands of robots?
I mean, I think it's important to appreciate that there are thousands of robot swarms operating out there. I mean, Amazon Robotics, I think, what was it last year? The Chinese light show had like 10,000 robots. There are certainly companies in the commercial world right now that deal with swarm-sized multi-robot systems.
Do we have a notion of best practice? Or are we still too nascent to have a notion of?
I think if I put on my like software engineer hat, I think there's something to remember about. You start pushing into that like 100 plus real robot kind of examples, and there are like significant like software delivery problems that need to be solved, just in terms of like making sure all of those things are actually running. I presume that companies like Amazon and Intel and others who deploy these large scale like systems have solutions to those, but I think figuring out what the community solution is to do something like that is certainly going to be an important part of that. I shudder at the thought of taking like a real stack for doing autonomy and making sure that the right version is running on even 20 or 30 robots is a big task for a lot of people. So maybe the answer, part of the answer here is like find friends. It definitely is the type of thing that will require lots of people. It's not something that one person's going to put their heads down and make happen.
Go back to our idea first. Go ahead.
Sorry, if I may, just maybe a slightly different idea. So if you really want to do hundreds or thousands of robots outdoors, off-road, it's definitely getting complex, right? So I was just thinking of okay, in water, if it's surface vehicles, okay, you maybe you catch them like fish once you're done, and then maybe you can collect them again, because you also don't want to put garbage into the environment, right? So you want to make sure you get all of them out of it once you're done. And so someday I was like daydreaming about like tiny agricultural robots that you actually send into the field, and then whatever we do currently with chemistry, they would like mechanically pick bugs from these plants, right? That would be a nice swarm robotics application, and having hundreds or thousands of them would help. But then I also thought like, okay, but each of them has a PCB, a battery, and so on, and you cannot be 100% sure that all of them will come back, you know. So how do you solve that? I have no solution to that, but it means like you need very, very high autonomy in these systems, especially energy autonomy, and then somehow, don't know, rely on them, that not too many of them break and you will have them back. Or you find ways of like, what is it? Like deploying them so that you later collect all of them again. And I think these are fun questions to think about. Definitely something we will have to do at some time in the future.
So on that note, our big challenge, our grand challenge, this panel discussion concludes. I want to thank all our panelists and our speakers. And so thank you very much for taking the time, and we look forward to the next part of the workshop.
All right, thank you, Annie.
Thank you.
Thank you for sharing this. Thank you to all the speakers for the riveting, enlightening discussions. Yeah, seems like we need an heterogeneous multi-human system to build multi-robot systems. That looks like the takeaway or the grand challenges. But all right, so I think now, Sid, it's time to move on to our next exciting part of this workshop.
Yeah, that is.
I'm gonna take it from here.
Yes, let me just share screen.
And maybe in the meantime, let's actually remind all speakers that you can go on the Q&A website, webpage of the workshop website to answer some of the questions that were not left unanswered during your talks, if you have time, obviously.
Yeah, definitely. That was wonderful. Okay, I think I can move things along here. This brings us to a very, very exciting part of the workshop, which is the interactive sessions. So here you'll have the opportunity to interact with some amazing swarm robotics researchers in a one-on-one or a small group setting. So we have 13 e-posters and 8 swarm robotics video demonstrations on display today, which were accepted out of all of the submissions that were made to our workshop. So the way this works is that each submission has been basically given a breakout room in Zoom. So here you can see how basically you can navigate to the breakout rooms. You should see it at the bottom right-hand side of your Zoom panel. So the breakout rooms are basically given by a serial number followed by the title of the submission. And you can also find the same information on our website under the interactive sessions tab. So you can correlate the breakout room number with let's say the paper or the poster PDF on there. But you can navigate into the breakout room and you can directly talk with the authors of that submission. Additionally, we have our corporate sponsors who have kindly sent our folks to talk about their latest products and offerings. So please check out breakout rooms 1 and 2 as well. to meet with people from Bitcraze and ClearPath Robotics. We're going to talk about their latest stuff. With that, I think I'm going to go ahead and declare the breakout rooms open. So everyone should see that pop up at the bottom right-hand side of their screen. Gennaro and I are here always if you need help, so don't hesitate to reach out to us. And enjoy the interactive session, and we'll reconvene here in the main room at 12:50 p.m. Eastern. Thanks.
See you soon.